This talk aims to introduce probabilistic modeling in Elixir using Stan and ExStan. Before we dive into probabilistic programming, we'll analyze a famous game show and its relation to probability. So the game show Let's Make a Deal was a famous game show run by host Monty Hall, where you as a contestant would have the chance to win a beautiful car. The game starts off with 3 doors. Behind one door is the beautiful car that you would like to win. However, behind the other 2 doors, there is a goat where you don't win anything. The game starts off by you making a choice about which door might contain the car. Suppose you choose door number 3. Next, Monty Hall will open a door where one of the goats is present. He will never open a door with the car behind it. Now, Monty Hall will offer you the chance to either keep your choice of door or change it to the remaining door that's available. And the key question is, do you change your choice? Does changing your choice even make a difference? It turns out, actually, it does. Changing your choice doubles the chance of you winning the car over a long run. This may seem counterintuitive, but you can actually work this out manually through brute force. It is correct to assume that initially each door has a 1/3 chance of containing the car. However, once the door containing a goat is opened, you need to account for this new information before calculating the probabilities. Monty Hall demonstrates surprises in probability. In real life, we have many more outcomes, making them even less predictable. Ideally, we like a system to manage this uncertainty through models, which are both accessible and usable. There are many use cases for probabilistic models, such as disease outbreak modeling, which measures how fast disease is spread, along with the effect of measures such as lockdowns on it. Marketing mix modeling, which aims to determine the most effective marketing channels for a company. And finally, advanced conversational AI, such as the recent large language model craze, which was made popular by the tool ChatGPT by OpenAI. Probabilistic programming is one such system to model uncertainty. In traditional computer science, we implement algorithms and rules to transform input parameters into outputs using programs. In statistics, we analyze data to interpret patterns and compute probabilities based on given parameters. Probabilistic programming, on the other hand, constructs models as programs that can generate data for addressing problems with inherent uncertainties. Probabilistic programming can be implemented in any language that has a random number generator, and it introduces a set of stochastic primitives. These primitives represent distribution over values. For example, this here represents that we have a variable x that is a normal distribution with mean mu and variance sigma. We can also have distributions over functions such as Gaussian processes, and we can also compose these primitives to make them dependent on each other, such as having a variable p and having a variable y dependent on the variable p. And the main aim of probabilistic programming is to use it for Bayesian inference. So what is Bayesian inference? The main workhorse of probabilistic programming is Bayes' theorem, and it describes the probability of an event given prior knowledge of conditions related to the event, which here we have the prior knowledge of the conditions related to the event, and here we have the probability of the event we're interested in. We'll now break down each term. So Bayes' theorem consists of 4 main parts. The first one is the prior, which represents information we already know about a problem. In Monty Hall, this would essentially be how likely there is a car behind the door. Likelihood represents the probability of observed data set given the set of parameters and hypothesis. Evidence represents the probability of observed data over all values. If the number of values is discrete, this would be a summation over all discrete values. If the values are continuous, this will be an integration. This is also referred to as marginal probability. Finally, we have the posterior, which represents the updated probability of our initial beliefs given the observed data. We can also write the Bayes theorem as posterior being proportional to likelihood and prior, which means that it's it's the value of the posterior is up to the value of the likelihood times the prior, but not equal to, because we skipped the normalizing constant. The graph represents how the prior likelihood and posterior distributions could look like after inference. The main problem with Bayesian inference is computing the evidence term. This is primarily because the evidence term becomes more difficult to calculate as the parameter space grows. And we need a way to simplify this computation. There are two main ways of doing it. One is using something called conjugate priors. These are essentially just a special combination of distributions for likelihood and prior, such that the posterior will have the same form as the prior. So, for example, if you use a Bernoulli distribution to represent your likelihood and you use a beta distribution to represent your prior, your posterior will also be a beta distribution with different values. The second common algorithm used is sampling. It aims to generate samples for a simpler distribution, which is easier to compute than the true likelihood, and uses these samples as an approximation of the true distribution. For example, if we run our sampling process to estimate what the Elixir logo looks like, we might end up with something like this. There are also other methods available, such as variational inference, which are primarily used when the models are very complex. While Bayesian inference is very powerful, the actual model development is a complex process. This is because there are many options of selecting priors and likelihood distributions. And without a system, this can lead to ad hoc decisions and discarded models. The Bayesian workflow aims to provide a systematic but flexible process to follow. It consists of three main steps. First is model building, where we incorporate prior knowledge that we have. The second is inference, where we perform sampling to get an approximate values for the distribution we're interested in. And finally, we have the model checking phase, where we check if the model is relevant for our data set. The workflow has been expanded into multiple other steps, as shown in the image on the right. And this was a paper by Andrew Gillen. Results from one stage may need revision of work in the previous stage. And this is an iterative process. And probabilistic programming languages help implement this Bayesian workflow. We'll now dive into each of these stages. The first stage involves incorporating prior knowledge in our models, which is modeling both the priors and the likelihood. There are a few common distributions used when creating Bayesian models. For example, a uniform distribution is used when all outcomes have an equal chance, such as tossing a coin or the faces of a die. A normal distribution is used when your values are in a bell-shaped curve. A binomial distribution is used when you want to model multiple trials of an event, such as the number of times you've succeeded in an event. The Poisson distribution is typically used when we have discrete values or values that we want to count, for example, age, number of clicks on a website, etc. And finally, the exponential distribution is used to measure time between events. The graph gives a brief overview of how you would select your prior. For example, if you have an event with discrete values and the data is equally distributed between classes, that means it's symmetric, and it's centered around a central value, a good choice would be a binomial distribution for the prior. We will now explore the inference stage of Bayesian workflow. And essentially, Markov chain Monte Carlo sampling refers to a class of sampling algorithms. These were introduced at Los Alamos in the early 1950s. This is the same place where the atomic bomb was invented. Breaking down these terms, essentially, Monte Carlo just refers to simulation, and Markov chains refers to a stochastic process, which is governed by the Markov rule. And the Markov rule states that the probability of the future value only depends on the current value, and the past does not matter. Represented in an equation, this means that at time t plus 1, the value will only depend on the value that was at time t. Every MCMC algorithm must be a special Markov chain, meaning it should be reversible. And this is achieved by satisfying the detailed balance equation. What this equation states is that if pi is a stationary distribution and pi x represents the chance of being in state x, and pi y represents the chance of being in state y, and p of x to y represents the chance of moving from x to y and y to x, The equation states that the chance of moving from state X to state Y should be the same as the chance of moving from state Y to state X. So the Metropolis-Hastings algorithm was the first practical MCMC algorithm and arguably the biggest contributor to adaptation of probabilistic modeling. It gives a way to build a Markov chain easily. Essentially, this algorithm samples from a target distribution, which is simpler compared to the true likelihood. And it works as follows. It first creates an initial value X. Then it makes a random proposal for a new parameter called X prime and a random value called U. And finally, it accepts this proposal probabilistically based on the chance of the new value. And if you look at this process graphically, what you will see is that on the left, we have a target distribution that's a mixture of two Gaussians or a Gaussian hill. And you're looking down on the Gaussian hill, so the maximum value is at the center. And you'll see that the Markov chain wanders around this hill, making random proposals and moving away from its current position. The green arrows represent accepted proposals, that is, chain moved to a new location, and the red arrow represents rejected proposals. As the number of samples build up, we start seeing the target distribution take shape. However, if our target distribution is a bit more complex, for example, if it's this donut-shaped distribution, we see that the algorithm struggles. A majority of the samples are rejected because they're made at random, and this wastes both a lot of time and a lot of compute. There must be a better way to do this. And Hamiltonian Monte Carlo sampling, or HMC sampling, aims to address this drawback of Metropolis-Hastings sampling. And you can think of our target distribution as this big n-dimensional surface, or very similar to a very large bowl. What HMC tries to do, it tries to do a physical simulation of particles in this bowl. And the idea is that if we flick a particle down this bowl, it will flow across the bowl, eventually turning around. And if we sample along this path before flicking the particle into a random direction, we will learn more about the surface. The image shows the path of a particle with the red dot showing samples that have been accepted. An easier way to visualize this is with a simulation. So back to our mixture of two Gaussians again. Here we see that the number of accepted proposals is much higher compared to Metropolis-Hastings. And even in the case of our difficult donut distribution, we see a higher number of samples. The cost of this algorithm is that we need more information about the surface of the bowl before we can be sure about the answer. Hence, this algorithm requires more compute compared to Metropolis-Hastings. Finally, the no U-turn sampling algorithm aims to improve the HMC algorithm even more. The main problem with HMC is that it requires that we specify the number of steps we take in our path before we execute the algorithm. This is a problem because if we take too few steps, then we'll get samples that are similar. And if we take too many, even then we'll get samples that are similar because the path will eventually make a U-turn. And NUTS aims to adaptively find the step size. It does this by simulating movement in both directions. It looks a little weird, but the key idea is that as soon as the algorithm detects a U-turn is coming, it stops the algorithm, generates a sample, and then randomly flicks the particle in a different direction. And this is the primary sampling algorithm used in many tools. The final part of the Bayesian workflow is validating our model, that is checking the trustworthiness of our model. There are two key metrics used to check trustworthiness: convergence plots and effective sample size. Convergence plots contain trace plots, which are used to assess convergence of MCMC chains. And here we are looking for something called mixing of chains, as shown in the image. What this means is that all chains have explored all values, and they've arrived at the same range of values. We also have the Gelman-Rubin statistic, which measures intra versus intra-change variance, and values close to 1 tell you that the model is a good fit. Finally, we also have effective sample size, which aims to quantify information lost due to correlation in your data. Meaning, if you have samples that are highly correlated, you ideally want to consider only a subset of those samples. Finally, we'd also like to check if the model is relevant for our data set, meaning if the distribution we've obtained is actually approximates our actual data set. So here we perform something called a posterior predictive check, where what we do is we simulate data from the posterior and then assess the difference between the posterior and the original data set. If the data set is large, or if the difference is large, we reject our model. You would then need to go back and refit the model, possibly with better priors or with more data. And if the difference is small, we accept the model. So Stan is a probabilistic programming language that helps implement the Bayesian workflow. It's a state-of-the-art platform for statistical modeling and computation. It primarily provides estimates through MCMC sampling via NUTS. It also has support for optimization algorithms using Newton optimization and BFGS optimization. And finally, it also implements variational inference and Laplace approximation, which are generally used when the model is more complex. Stan has been primarily developed in academia, but it's actively used in industry. On the right, you see other alternatives to Stan that I've used. There are many more that I've not covered here. And most of the tools here, again, are in the Python ecosystem, with PyMC having a large amount of adoption. Stan has a few key features. First, a Stan is strongly typed, so every variable must have a type. Stan natively supports vectorization, which helps speed up computation of operations. And finally, Stan is a compiled language, so models are first translated to C++ and compiled to machine code. So this reduces overhead and allows compiler optimizations, but the disadvantage is that we require more resources and the C++ toolchain. Stan's syntax looks as follows, where we first we specify types for each variable. We can also specify constraints for each variable, such as upper bounds and lower bounds. So for example, a Boolean value could be lower 0 and upper 1. The Stan model specification has 4 main blocks: data, which is used to represent the data for the model; parameters, which are used to represent our parameters for the model; the model itself, which contains both the definition for the prior and likelihood; and finally, generated quantities, which is primarily used to sample from the posterior to generate posterior predictive checks. There are many more optional blocks that we've not included here for brevity. ExStan is a lightweight SDK to interact with Stan and Elixir. It depends on HTTP-Stan, which is a shim that enables Stan interaction via HTTP. HTTP-Stan also supports caching and parallel sampling, helping improve inference speeds. And the flow on the right shows the life cycle of modeling the request with ExStan. We first define the model and do some validation, send a HTTP request to the HTTP-Stan server, which compiles it to C++ using the Stan compiler, runs inference, and returns the result, which we then process. Now we move on to a short demo. So here we will aim to perform simple linear regression using Stan. We'll also aim to look at performing simple checks to see if our model is accurate. The dataset we select is the iris dataset, which essentially consists of 150 records and 3 classes, 50 records per class. These records contain the sepal width and length and the petal width and length of 3 classes of flowers. And let's assume that we would like to model the relationship between sepal length and petal length for the setosa class of flowers. For the sake of simplicity, we'll assume that this is a linear relationship defined by the equation y equal to alpha plus beta times x plus epsilon. Here, x is our input data or the sepal width, y is our output data or the petal length, alpha is the y-intercept, beta is the slope, and epsilon is the irreducible noise, which we assume comes from a normal distribution with mean 0 and variance sigma. The key assumption here is that we assume y scatters around the linear line alpha plus beta x, meaning the distribution of y is given the parameters and the input is a Gaussian distribution with mean equal to this line and variance equal to sigma, as represented here. And what we can do is we can use Bayesian inference to find all lines and scatters consistent with the observed data to obtain the parameters we are interested in, meaning the parameters alpha, beta, and sigma given x and y can be obtained using the Bayes rule we've seen earlier. So we first get the data set using SciData. convert this into a data frame using Explorer, you would see here that there are 4 key features and 1 class: sepal length, width, petal length, and width. What we do now is we like to visualize the relationship between sepal length and petal length for the setosa class. We see here that indeed we have some noise in the relationship between sepal length and petal width. We'll now store the values for X and Y, which will be used as input for our model. Next, we'll actually define our model. So this is the part where we encode expert knowledge about our domain. So if, for example, we were confident that the value for alpha or the y-intercept is normally distributed with mean 3 and variance 1, we could represent this with a prior as normal distribution 3, 1. For now, let's assume we don't have enough domain knowledge. So we're going to cast a very wide net of parameters. This is also called as assigning weakly informative priors. And this will increase the chances of us getting the right parameter. So the model code looks as follows. In the data block, we define the input parameters, which is the number of points, the sepal length, and the petal length. The parameters define parameters of interest, which is alpha, beta, and sigma. And the model defines first the priors, which we all assume are normal distributions, and the likelihood, which also comes from a normal distribution with mean alpha plus beta times x and variance sigma. We'll now give the input and build the model using ExStan, which will essentially return an object of type model. Now we will perform inference and we will sample from our model. We will sample using 4 chains, and we also have certain additional parameters. For example, we have a num warm-up parameter that refers to the number of samples considered as warm-up. So the initial samples generated will be discarded before we do any analysis. And finally, we also have parameters such as step size. So once we run the sampling, we can now run sampling. And what we will get as output is a struct of type exstan.fit. There are the key attributes here are stan outputs, which is the actual JSON output returned by the stan compiler. Feature names, which is the list of all features returned. So this includes alpha, beta, sigma, along with a few diagnostic features. And finally, an attribute called draws, which is an NX tensor of shape, feature names, types, num samples, type num chains. We'll now evaluate our fitted model to check if the model is trustworthy. First, we'll check for chain convergence using a trace plot. So we'll convert our fit object to a data frame and then visualize the trace plot for the alpha parameter. What we see here is that all 4 chains have mixed it well, and they've all arrived at a similar stationary distribution, showing that the model has converged. We can also calculate the Gelman-Rubin statistic, which measures interchain versus intrachain variance. Finally, we can also look at some summary statistics for the attributes generated. Here, we see that there are many additional parameters explained. The key parameters to look at are LP underscore, which is the log probability. This is primarily used for debugging and model comparison. The divergent underscore feature, which is a binary indicator telling if an iteration experienced divergence. And all the other parameters are sampler hyperparameters, which you can tune. Next, we look at what these actual parameters returned from Stan are. So we will first create a forest plot, which will help us display point estimates and confidence intervals for our parameters. Here we see that alpha has a mean value of 0.2, but it has significantly high variance. And what this means is either our priors are bad or we need to incorporate more data to get lesser amount of uncertainty. We're more confident about the values for beta and sigma. Finally, we look at our posterior plot where we'll aim to create the line or the linear regression line obtained using the parameters we got from Stan, that is using the mean values for alpha, beta, and sigma. And when we plot this, we see that the linear regression line is actually a pretty good fit. We can also get the posterior interval by plotting all posterior draws to get the uncertainty estimate or the confidence range. Finally, we'll also perform a posterior predictive check where we'll aim to simulate data from our posterior distribution, that is, perform posterior predictive checks. Here, we'll aim to measure if the model performs a good job of capturing relevant aspects of our data. So what we will need to do is we need to use the generated quantities block. So we'll redefine our model same as it was before for data parameters and model. And now our generated quantities block will have a vector called ysim, which stores the simulated data from the posterior. And then we generate n samples using the parameters that we've estimated earlier. We will refit this model, convert this to a data frame, and plot, compare the distribution with our original data set. So say we compare the distribution for 5 samples. You see here that the line in black is our original data set, and all these are samples that we've obtained. And you see that these posterior samples are a very close match to the original data set, indicating that our model has achieved a good fit. If the posterior is not a close match to the original data set, that indicates a problem with our priors and our specification. A second case study that we can look at is the FIFA World Cup 2022. Essentially, we want to estimate the outcome of football matches here. This model was created by Professor Leonardo Vecchiti and Vasilis Palaskas. And it contains data for each team from 2018, including the number of matches played, goals scored, global ranking. A subset of the dataset and its features are shown here. The model itself has 5 key components. First is team dynamics, which accounts for win, loss, and draws in matches. This is implemented as a Bradley-Terry pairwise comparison, which is represented here. You can read this as the probability that team I will win when they're playing against team J. The second component is team strength, where we measure team strength in both attack and defense using metrics like number of goals scored and conceded. We also allow team strength to vary over time to account for form. The third is ranking, where higher ranked teams should have a higher chance of winning. Fourth is draw probability, where in football, unlike other games, the chances of having a nil-nil draw are higher, and we like to encode this into the model. And finally, we have some zero-sum constraints, which aim to balance team ability over time, meaning the sum of their attacking and defensive strengths of a team is 0 at each time point. And this ensures that we don't get multiple sets of parameters that fit well. We only get a single set of parameters that fit well for our problem. So the model itself consists of these equations. The key part here is that this is a diagonal inflated bivariate Poisson model. Breaking this down, Poisson essentially is used to count the number of times a specific outcome occurs. Here it's used to count the number of goals. Bivariate means that we count the number of goals both for the home team and the away team. And diagonal inflated means that we use a modification of the Poisson model that allows for nil-nil draws more. Looking at the equations, the first 2 lines, xi and yi, represent the random number of goals scored by the home and away team. In the event that there is a draw, d represents the probability of having a draw. If the goal scored by both teams is the same, then we add a term to account for a draw. And BP refers to the Bradley-Terry paired comparison. We model individual scoring rates for both teams using lambda1 and lambda2, which are dependent both on the ranking and the attacking and defensive ability of teams. We also have another parameter for tracking score covariance, meaning the relationship between scores when 2 teams are playing. And the attacking and defensive strengths of teams are initialized to account for changes in performance over time. Finally, we also initialize certain priors, which are just assumed to be obtained from normal distributions. And then we add some sum to zero constraints. Here, essentially, what we do is the sum of all teams' attacking strengths and the sum of all defensive strengths for each team are constrained to be equal to zero. This balancing act helps in centering the parameters around zero, providing a more stable and interpretable model. And centering around zero makes it easier to interpret strength as above or below average. When we can define the previous model in Stan and run inference, and after fitting, we get the following results as shown in the table. The table here shows the chance of win, loss, and win and draw for both home and away team. Here, MLO refers to the most likely outcome. On the right, we see a graphical representation of this table. We see that Argentina was expected to beat Saudi Arabia, given their strength and their form. However, we also see a small probability assigned to Argentina losing 1-2, which was the actual outcome. And a betting man could use this model to increase their chances of a payout. Finally, once these matches have actually been played, we can incorporate the results of these matches into our model, along with additional priors to improve our modeling going forward. Coming to the limitations, the biggest limitation of Stan is that HMC requires continuous parameter spaces. So even you can't do inference on discrete parameters, meaning parameters that take only integer values. As the model gets more complex, the parameter space also increases exponentially, which slows down inference. And Stan itself only has experimental GPU support, so it can't really take advantage of GPU compute as other models can. For upcoming features, we plan to add support for other sampling algorithms such as variational inference, which are not natively supported in HTTP-STAN. We also aim to add support for RVIS, which is a package that simplifies generating model diagnostics and metrics. So an example of this is a rich plot which shows the estimate of defensive ability for football teams. We can create this with Vega Lite and Kino as well, but it's a bit more work. And finally, we'd also like to add case studies to demonstrate the power of probabilistic programming. The key takeaways here are, first, Bayesian inference considers prior information when making predictions. The confidence in these priors, which are determined by domain experts, will influence your output up to a certain point. And the ability to use weak priors and rely solely on the data is a superpower of Bayesian inference. Bayesian models are not data hungry, and you can get a decent model with a relatively small amount of data, but good priors. And we also get uncertainty estimates for each parameter, which makes these models more interpretable. Finally, there are a set of resources we can look at to learn more about this. The first is the Bayesian data analysis book by Andrew Gellman. And one of the foundational models responsible for the LLM revolution, GPT-2, has also been implemented in Stan by Daniel Lee, which is available as a tutorial. And there are also many real-life case studies available on the Stan website. And this concludes my talk. Thank you.